from AutoWorks and the other one from IBM. Before I introduce the speakers, I want to pass the mic to Sarah and Bob to talk about the GoPro.
Hi guys, I'm just gonna set up. Actually, I'm gonna set up a computer really quick. Just make sure I can set this up. Well, welcome everyone. Hi, my name is Sarah Mangiano. I'm a recruiting specialist here at GoPro. I will use the mic, sorry. I've been here for about 1.5 years, and so I actually help support all of our US departments along with Europe. So I'm just here to talk to you very quickly about our recruiting program. So I could probably talk for hours about how amazing all of our teams are across the world, but I'll keep it short for about 2 minutes. We thrive in an extremely collaborative environment. We actually have some of our employees throughout the room, so feel free to meet them afterwards. But I'll go through quickly. This year has been absolutely amazing. I don't know who's kind of kept in touch with what we've been doing, but over the last few years, we recently just launched about 2 weeks ago 3 new products, well, new-ish, our Fusion, which is a 360 camera, our Hero 6, and then we've added additions to our GoPro app. But with that being said, we couldn't have done any of that without our amazing teams. So most of the people in this room right now are in engineering. So these are actually current positions that we have up right now for our teams in San Mateo. But with that being said, if you guys have any friends, family, we have tons of positions open across the board. So marketing, IT, other engineering positions across hardware, also in our San Diego office. So feel free to check out our GoPro page. We have tons of positions open for you guys to take a look at. If you are interested in any, I highly suggest applying directly online and just mentioning that you came to this event so we know exactly how you found out about us. Unfortunately, I cannot stay too long today, but I will give my information to Chester and he can share it with all of you afterwards, so feel free to connect. Thank you. Also, anyone that sits in the front gets a t-shirt or hat. So, just saying.
Well, you got a plan?
And I just want to take a minute. So.
Yes.
Thank you. So I'm Bob Carlson, I'm Director of Product Management for our software platforms here, and one of the positions up there belongs to me, and I'm looking for someone who can really kind of come in and bring a lot of big data experience and kind of help guide the nature of our platform and how we can really add value to the company. We've got a really interesting situation here. We're talking software, behavioral data, hardware data, sales, finance, marketing. All of it is kind of coming together under Chester's platform, and we really want to kind of help guide that roadmap. So if you have any interested people who might be able to contribute, please send them our way. We got some awesome advantages here that we're looking to take care of. So, thanks.
Thanks, Bob. Thanks, Sarah. Yeah, as Bob said, I actually the head of data science and engineering teams. So if you, I don't have a position right now, just filled it, but other team does, and also including the cloud teams, the media teams, and other teams. And so if you're interested, just talk to me afterwards. Okay, so with that, let's introduce the first speaker. Wanda is work for HADOOP. He's the Apache committer and the PMC members. And he has been working for Hadoop Yarn for a long time. So I actually invited him to talk. I forgot it was a year ago at when I worked at the last company. He went to a tech talk about the newest features in Yarn. It's always a great talk. So this time today he's going to talk about TensorFlow in Yarn. So I'm looking forward to that talk.
Hi. So I'm Wanda, and I'm from Hogwarts, and I'm Apache Hadoop PMC member. Currently, I'm leading the scheduler and the GPU development in Yarn. And thanks GoPro for hosting this event. Yeah. So today my topic is to talk about how Hadoop ecosystem to boost the TensorFlow and machine learning technologies. This is the agenda today. So first, I will talk about the overview of the machine learning in real life, and I will talk about how YAR to boost machine learning workload, and we will talk about how to do a click-through rate on a big data platform. The last is a short demo. So first is how an overview of machine learning in real life. Yeah. So first, you may get a cluster with shiny hardwares, and you will have the storage. It could be HDFS, S3, or MySQL. So you store your data into the cluster and the storage, and then you may store the machine learning or the big data libraries like the Hadoop, Spark, or TensorFlow. And you need teams. First team is on the left side. It is a data scientist. So what they do is they will explore data and they will create a pipeline and they will find the best parameters. And once this is done, they will get the best demo they have been exploring so far. So they will save the demo and save the model to the cluster. And on the right side, it is software engineers. What they typically do is to load the model, and they will deploy the model in production. And once this is deployed, we can get an online scrolling or offline scrolling on the batch or streaming data. Yeah, so this is one paper from Google. It is called Hidden Technical Debt in Machine Learning Systems. So if you look at this picture, the machine learning core, it's the middle part, is the smallest part. Yeah, so it is a core of machine learning algorithms, which is a TensorFlow, for example. And besides that, there are lots of complexities. For example, how to do the compression, how to do the data collection, how to do the feature extraction, and how to do for example, the machine resource management. All these things are very complex, and we need all these steps to make the machine learning can run well. Yeah, so I will briefly talk about the machine learning workflow. Yeah, so first is the data pre-processing and feature engineering part. So everything comes from data. So on top of the basic the raw data, we will do the ETL, and we will do the feature fetching and feature encoding. And once this is done, we will get the features which we extract from the data. What we are going to do is to feed these features to the model training and model evaluation and model staging. So basically, we will train the model using machine learning algorithms by using the features. And the last part is online service. So basically, once the model is generated, we can serve this as a service, or we can, based on this model, to do more experiment. So let's go to the first part, and let's zoom in. The first part is data pre-processing. So typically what we do is we need to import the data from storage. It could be HDFS, AWS, or some DB. And we are going to operate on the data. For example, we can join the data, use Hive or Spark, and we can do the data exploration using zipping or Jupyter, for example. We can show in the basic, for example, the basic histogram of the data, and we can do some sampling of the data to do some experiment, and we can do using for example Spark to split the data to the training set and the test set to do the training. And once the data pre-processing stage is done, we will go to the next phase. it is a feature engineering. Yeah, so for the feature engineering, the old way to do this is to manually to design the feature and but sometimes this doesn't work very well. So the deep learning can make the feature engineering to be simpler. For example, this is a machine learning training for the face detection. So on the most left side, it is from the raw data, and the deep learning algorithm for the first layer can extract some basic features, for example, the edges and the shadows, for example. And on the second stage, they can extract some more complex features, for example, the eyes, the nose, and some other important piece on the face. And on the last phase, it becomes the actual the human's face. Yeah, so I can talk a little bit about the model training. The model training is, we have two different categories. First is some traditional machine learning models, for example, the logistic regression, the gradient boosting tree, and the SVM and LDA, for example. And we can use libraries like the Apache Spark, MLlib, and the XGBoost to do the trainings using the traditional machine learning approach. And on the other hand, there are some new deep learning models, for example, DNN, CNN, RNN, and LSTM. And we can use the latest libraries like the TensorFlow and MXNet or PyTorch to do the training. Yeah, so for the model training, the deep learning cannot fit all. So basically, we have lots of machine learning tasks. For example, the natural language processing, computer vision, speech, video, anti-fraud, and recommendation. There are lots of tasks. For the deep learning, sometimes it works well on some of the tasks. For example, the deep learning works very well on the computer vision part, but for some other parts, it may not work very well. So in the practice, we still need to compare it with some traditional machine learning workload and see which one can get better result. Yeah, so the last part is the model serving. Basically, we will just take the model out and use its existing frameworks to serve the model. For example, we can use Spark to load the model trained from TensorFlow to do some batch scoring, or we can just launch the TensorFlow serving service on the cluster to do the online model serving. Yeah, so I just quickly go through the overview of the machine learning in the real life. The second part is how the Apache Hadoop yarn to boost machine learning workload. So I will first talk about what's the machine learning plus big data platform on yarn looks like. The first is we will get some hardwares on the bottom. We have maybe CPU, GPU, and SSDs on the cluster. And we have storage that's set up on top of the hardware. And we can install Hadoop yarn to manage the resource and also can load data from the storage. And we can deploy some batch job or the SQL frameworks like the Hive ALAP or the Spark SQL to do the SQL operations. And also we can deploy the machine learning libraries, for example, Spark, XGBoost, and TensorFlow to do the machine learning workload. And we can deploy Zeppelins to let the data scientists can easier digest to explore their data. So here's the question: why we put all under yarn? This is a normal yarn user we see almost every day, and they want lots of things. The first thing is they want SLA. So basically, they want their job can be launched at some given time, and they want their job can be finished within some given time. And they want better monitoring. They want to see what's the stage of the job, and they want to see why my job gets stuck, or why I cannot get more resources than some other user. And they want isolation, so they don't want the jobs from other user or the jobs from the same group to affect each other. So for the SLA, we have capacity planning. So basically, we can set up the queues, which can serve as a hierarchy. For example, for the engineering department, they can have 50% of the cluster resource, and for the developer team, they may have 20% from the engineering group, and QE team maybe have 80% of the cluster resource. Once this is get planned, so they can submit jobs to different queues to get different resource. And we also have preemption. So if someone takes more resource than they guaranteed, we will the yarn scheduler will kick in to kill some tasks to make the user can get enough resource. Also, we have a reservation system which you can reserve the resource before you submit the job, and also the latest feature has you can do the periodically to do the reservation. For example, you can reserve. I have a job which will run at 3 a.m. every day, and it's some resource. And for the monitoring, Yarn recently added new timeline services which you can view and get all the history data from the storage. And Yarn can integrate with the Grafana's, etc. to get better view of the resource. And for the isolation, we can do the isolations on the CPU memory, and also the GPU isolation is work in progress, and I can talk about this later. And some more are to be added. Currently Intel is working on the FPGA isolation, and the network is also on the planning list. So Yarn is the most popular production-ready platform to support both of online and offline service. So you may not be able to get this from, for example, Mesos or Kubernetes. You cannot get they to support the offline workload very well. Yeah, so this is an example about how we all running these stuffs on the same platform. So let's say we have a 5-node cluster. Each of them has 128 gigabytes of memory, and they are managed by Yarn. First, we can deploy, we can run in some test job, to run some high queries on the cluster. They will be allocated on some of the node and start running. And we can run Spark, which will run together with the test job. And we can deploy some long-running service, for example, the HypeL AP to do some interactive queries. And the department may get some more budget, so they added GPUs to the cluster, which we will also add these GPU machines to Yarn to manage. And we can run TensorFlow by using this GPU machine. When the user wants to request TensorFlow to run the GPU machine, we will directly allocate the GPU resource for these tasks. And also they can run, for example, Caffe or the MSNet to consume the GPU resource together with TensorFlow workload. Yeah, so I will briefly talk about the GPU support on yarn. First is why we need the GPUs, why we need to run the workload on GPU. Because GPU has many cores which can handle the massive but much simpler computation tasks simultaneously compared to CPU. So on the left side it is a GPU, it has many cores, and on the right side is CPU, it has less but more powerful cores. Because for the deep learning workload, they are mostly the matrix computations. So these computations can be optimized when we run this on the GPU. So we can put the computation to two parts. One is the GPU computation intensive, which can be optimized by using GPU, and the others we cannot see much benefit by putting this to GPU. So once we map this to the once we run the job, and the framework, for example, TensorFlow, will directly map the GPU computation intensive part to the GPU. And when it is get started, the GPU part becomes very can be done in a very short time. So the overall job performance can be improved. So without GPU support, the researchers or engineers are almost impossible with job to finish, because it will take several months to train some large model. It is impossible to wait for such a long time. The GPU support on yarn currently is on track, and the ETA is Hadoop. It will be released with Hadoop 3.1, and which is planned at the January 2018. So this is a new UI added for the GPU support on yarn. So I'm working on this recently, so I just post some work in progress screenshot here. Yeah, the second part of new added to yarn, which can help the machine learning or some other general services, we call it yarn service assembly. We can make, by using this, we can make everything much easier. So I'm not sure how many of you have tried to write yarn application master before. No? Yeah, so seems you are very lucky. So writing application master on yarn is super hard. So that's why we got several frameworks natively running on yarn. For example, the MicroViews, TED, Spark. So it is very hard if you want to implement something to run it on yarn by using the native application master API. It will take a lot of effort. What we do is we added the native service, which you can directly write in an assembly spec in JSON. We call it yarn file. And by submitting this file, we can get the service running. This is very similar to the Marathon or Kubernetes. Yeah, and we will post the JSON as a REST request to the yarn server, and the yarn will figure out the rest of it. So here's an example. This is a TensorFlow training example by using the yarn assembly API. First we will define the name of the job or service. Now the name is TensorFlow training, and it has one component called TensorFlow trainer. And there's no dependencies. So later I will talk about how we can use this to run some jobs in stages. And for this trainer, we have only one container here, and we will specify the artifact, which is a Docker image name. And we will specify the launch command, and also we will specify the resource. In this example, we specified 16 CPUs and 32 GB of memory and 4 GPUs. So this one, the ETA is Hadoop 3.1 as well. So it is actually should be 2018 January. Yeah. So I will talk several more examples about how yarn assembly to run multi-stage jobs. this is one job which has two stages. One is to run in the Spark preprocessor first, and it will run 5 container Spark job, and it will run the launch command to do the preprocessor to launch the job. And then we can specify the other component, which is a TensorFlow training component, and put the Spark preprocessor as a dependency. So once the first is finished, we will start the second one. And this one is an example about how to run the distributed TensorFlow training with parameter server. So we will have 2 components. The first component is a trainer. We will specify the trainer to use 10 containers. And this is a launch command. We will specify the command, and for some unsure part, we can use the trainer 0 to 9 to nodes to represent the 10 trainers. And for the second component, it is a parameter server. We can launch the parameter server. Also, we can use yarn assembly to do some more steps. For example, the parallel parameter tuning. So basically, we can write several trainers at one batch and submit these things all together to yarn. And all these trainers will get started when the cluster has enough resource, and we can monitor the training progress separately for these trainers. And also, we can use the yarn assembly to do model serving. This example is to run the do serving script, and we can specify what's the model we want to serve. Here is using the Inception v3 model, and it will expose a port, so we can connect to the port to get the model serving. Also, when we specify the number of containers, the yarn can figure out how to do the load balancing in the backend. So when we come this is the host name. When we come to the serving.tensorflow model serving and some domain name, the yarn will do the load balancing to choose one of the serving service to get the result. Yeah. Also, when we can imagine once we have the model file to be updated, we can replace the existing model file and just to do the upgrade of the images or the models. Yeah. So here's an example walkthrough about how to do the CTR on a big data platform. So here's a short introduction of the CTR prediction. So first we will, for the CTR, it is given a user and context. We will predict the probability of a click for an ad. And this is the most profitable machine learning problems. So lots of companies are investing in this. And there are some challenges. First, is even if it's a simple binary problem, but what we want is not the predicted class. We want the probabilities about how much the user wants to click the ad or not. And typically we have very skewed label distribution. So only few users will click the ad. For the rest of the users, they just ignore these ads. So for the skewed label distribution, it's very hard for the machine learning to create some issues for the machine learning. And typically, we will have tons of data because we have so many users to generate the data. And we need to predict very quickly. We can't wait for 5 seconds to get the result. We want to get the result when the page is finished loading. Yeah, so this is example of the data. For each entry, we have the impressions. The impressions, which is the context. We can think, for example, the cookies is one kind of impression, and the result is clicked or not clicked, and they are all labeled events. We can use these events to do the model training. And here's the models typically we are using to do the CTR model. The most common are still the logistic regression to do the CTR to do the CTR learning. For example, the logistic regression SGD and LBFGS. And also we have some newer models like the factorization machine and the GPT and the deep learning networks. So by using Zeppelin, we can make the Spark and some other libraries. For example, the TensorFlow can work together to do the CTR prediction. The Zeppelin can also be launched by Yarn. We can running a container which hosting the Zeppelin server. We can log into the server to do whatever we need. So first is we can use the Spark to import data and do some data exploration. We can import the data from some HDFS folder, and we can count the clicks to get how much times we get the user click on the data and how much time we get the user not click on the data. And we can do the sampling the data. We can only get some part of the data out and do the continue processing the data. And we can using the Spark to do the join and remove some NA values. And we can split the data to training and test set. Also, we can write the TensorFlow programs to directly on the Zeppelin to do the data to train the model. And we can also write a trainer by using Spark MLlib and compare the result. Also, we can use the sharing functionality provided by the Zeppelin. We can share the notebook from one user to another, and they can continue explore the data. Yeah, so I can play a demo video, which I recorded last time. It has 4 NVIDIA Tesla P100 GPUs. Start from here. Yeah, so here's a little bit background. What the demo taught is to using Yarn to manage a cluster which has GPUs and CPUs, and we are running the 2 jobs on the cluster. One is using GPU, and another one is using CPU, and we compare the result. On this machine, it has 4 NVIDIA Tesla P100 GPUs. In addition to that, this one has a CPU. It has 160 CPUs in this cluster. So what we are going to do next is to submit 2 jobs to the cluster. One will use GPU and CPU at the same time, and the other one only with CPU. We will compare the performance gain we can get from the GPUs. So this software is Postman. It's a better way to submit the REST request to Yarn. And once we have the job select ready, we can use the REST API to go to Yarn, so I knows how to match it. So for the first one, we will look at it's a CPU job. Because we will give the name of the job. let's go to the new UI to check. These two jobs should be already get started. And the first one is for the CPU, and the second one is for the GPU. Both of them are in the running state. So let's check the ones. So on the left side, it is the output from the job which is using CPU only. And on the right side, it is a job which is can use both of the CPU and GPU. So we can see that on the right side, it is already finished almost 200 iterations. And for each iteration, it takes only 0.4546 seconds for each step. And on the left side, it is just finished the first step. And for each step, it takes 63 or so seconds. So it's almost 100 more times faster while this job is running on the GPU task. Yeah, so that's mostly my today's step. Thank you. So any questions?
So I know TensorFlow has, when you have GPUs available, CPUs, sometimes you can actually manually direct what data you're sending to what type of processor. How are you doing that with Yarn? Is Yarn making those decisions for you, or are you still able to?
Yeah. So basically, what Yarn do is when the user comes to Yarn, it will ask how much CPU needed and how much GPU needed for every trainer process. And when Yarn launches the process, it will make the process to be isolated. So that means when the process gets started, they can only see the resource which are allocated to this process. Right? So when the TensorFlow process gets started, it will look at what's assigned to the TensorFlow process, for example, 2 GPUs plus some CPUs. It will map the operations on whatever are available to this TensorFlow process. Yeah, so basically you cannot use the resource which are already assigned to others. If we launch two TensorFlow process on the same GPU, we will likely see the out-of-memory issues.
So how do you compare it to TensorFlow on Spark? I think the TensorFlow on Spark, the RDE, distributed data to different TensorFlow on different nodes. How does it compare to that?
Yeah, so for the TensorFlow on Spark, it is the user experience is still very similar to Spark. The user actually it is a little bit weird to the end users. There are only few users are actually using the TensorFlow on Spark in their production. And the TensorFlow on Yarn is most like the native experience. It makes no difference from running TensorFlow on the Mesos or running TensorFlow on the Kubernetes. You will get the similar experience.
So you said that one user take too much resources and schedule very convenient. So how does it measure the resource? What does it measure?
Yeah. So I'm not sure. So your question is about when Yarn will come will kick in to do the preemption.
Yeah, based on what metrics.
Yeah. So basically, based on the allocated resource. For example, when for the Yarn queue, you can set up capacity, which is the guaranteed resource to you, and also you can set up max capacity, which is the total amount of resource you can use, but we cannot guarantee it. So if we submit jobs to a queue which is already above its guaranteed resource, the Yarn will look at the available resource in the cluster and give to you when at that time the resource is available. But if someone comes in to ask resource from some underutilized queues, the yarn will preempt the overused queues. So basically, it is based on the based on allocated resource. And there are some new changes in the yarn, essentially available in 3.1 or later. So that one is it will look at the actual resource usage. So if someone comes in from an underutilized queue, and all the resources are booked but not fully utilized, this is actually the common case. So the user will ask for more resource, but in the real program, they didn't use all this resource. So yarn can leverage this part of resource to launch your process. And this also avoids some unnecessary kill of the process.
My understanding is one of the advantages of Spark is in-memory processing, which gives a lot of performance. So does Yarn gives the performance or reduce the performance that Spark has?
So basically, Yarn is only manage the resource. So we can run the Spark applications on Yarn, which the Spark can ask some resource from Yarn and launch the process. So basically, Yarn will not do anything regarding to the computation. Yarn is just to serve in these computation platforms. And you can run Spark, you can run TensorFlow, and you can run MapReduce. There's no difference in Yarn's perspective. Yeah. Also, I forgot to mention one thing, which is a question from Chester. So you're asking the difference between TensorFlow on Spark and TensorFlow on Yarn. The biggest difference is that TensorFlow on Spark doesn't support GPU.
There was a graphic early on that seemed to suggest that if you used Yarn, then you could make optimal use of the GPU. Are you saying that you get some speed up running TensorFlow under Yarn?
So actually, it gets speed up by using the GPU. So what Yarn provided is it can more smartly to manage these GPUs. It will give you better GPU isolation and give you better GPU management. Also, you can boot the resource before you arrive to get the GPU resource.
This integration, when you start the TensorFlow workflow, does it reserve the whole resource, from the very beginning and keep it all the way until the TensorFlow flow finishes, or it split the task into smaller chunks? And especially for the GPU side, when it actually uses it, it dynamically allocate those resources and freeze it up.
So this is a very good question. So for the GPU usage, currently it is the time we allocate GPU is same as the time the process is running. This is because the TensorFlow itself cannot. So unless the TensorFlow can give a GPU use, we cannot take the GPU to other applications, right? If we take the same piece of GPU to the other application, but TensorFlow says, I want this GPU, the out of memory can happen.
So then if this training work runs for example, like a week, then during that time, this cluster, that part of the resource is going to be fully occupied?
Yeah, that is true. And also, because the TensorFlow is so intensively to use the GPU, it is actually very hard to give up GPU usage in the middle time.
So I think what I'm still not getting is, so if I have a cluster of CPUs and GPUs, and I have TensorFlow written, and in TensorFlow I specify I want this, these computations going to CPU, these computations going to GPU. I can do that today in TensorFlow, and I don't need Yarn to do that, right? So what does Yarn by me? And so that's where what I'm trying to make the link.
Yeah. So basically, what Yarn gives you is to make the different applications can coexist in the cluster. Right?
Okay.
So otherwise,
just multiple applications.
Yes.
Okay.
So for example, if you only have one GPU host, it is very easy to manage, and you can manage manually to launch the jobs. But if you have 100 GPU machines, actually we see some customers in that case, 100 GPU machines, and every machine has 8 GPUs. In that case, we have to use some framework to manage this GPU instead of manually do that.
Okay, thank you.
And to ask the obvious question, how does this compare to running Kubernetes?
Yeah, got it.
That's the question, compared to using Kubernetes for cluster management.
Yeah, so this is a challenging question. So for the Kubernetes, the pros of Kubernetes is it has better support of the Docker container, and currently we are trying to fill the gap. But for the Docker container user experience, if you are so intensively use Docker container, maybe Kubernetes is a better operation, a better option. And for YARN, it is mostly very good for the running the offline workload and the online workload on the same cluster. So because it has many ATOS securities, and it can also can deal with very fast job allocation. For example, if you want to run a macros job with 1 million of tasks, YARN can give you all the containers in less than 1 minute. But for the Kubernetes, it will take a long time to get launched. So in the largest YARN cluster in the world is in Microsoft. They have a 40K nodes cluster. But the largest Kubernetes cluster, if I remember correctly, it is only a few thousands. And because it is running the long-running service, the number of allocations for every second actually is very low, because for the services it gets launched, and typically you don't want to shut it down. But for YARN, you are consistently get the job to be launched and stopped.
So for often in the GPU computation world, you need to pin the memory on the GPU, which means you have a startup cost associated with your job. So you actually want to launch a service and keep it on that GPU physically.
Yeah. So for the YARN, the currently isolation of GPU is no difference from how the Kubernetes do the GPU isolation. Basically, before starts the process, it will pin the process to one or more GPU process, and they will these GPUs can be exclusively used by the process.
So there's no CPU using in the second, right? It's just for GPU.
No. So basically for the two jobs, they're both using CPU, but the second job using CPU plus GPU.
So what if the second job or the third job doesn't use any CPU? Would the time be a little?
So basically for the TensorFlow, even if it is very intensively used GPU, but it still must to have some GPU to have some CPU resource to run the other operations other than the GPU intensive part.
Yeah, so this one up, my question about you talking about multi-stages job for YARN. For the current version, like how many parallel versions can you do for a job, either with any size of cluster, and if there's a limit, how many clusters you can do?
So your question is how many stages we can specify?
Yeah.
Actually, we haven't tested that. But yeah, so typically, I think for the most use cases is several stages, because this spec is specified manually, right? But if we want to support some dynamic specify some stages, we haven't think about that yet. Yeah.
Great, thank you. Thank you very much.
Thank you for that.
Well, we have a second lightning talk. This is going to be a quick introductions from IBM's. It's Mike and Madison from the IBM Spark Technology Center. So they're going to give you a little introductions of what they're working on, and I think either next month or the month after, I don't know. I haven't talked to him about the schedule yet, but it's quickly going to do a full talk for the research work they have done.
Thank you.
Thanks so much, and that was a great talk. Thanks for that as well. All right, so this is Mike, and I'm Madison, and as we were introduced, we're from IBM Spark Technology Center. Thank you. And we'll be talking about mitosis detection today, so it's pretty exciting. So a little bit about the Spark Technology Center. We were founded a few years ago. We're located downtown San Francisco, next to the San Francisco MoMA. Great location, stop by. So our main mission is basically to contribute intellectual and technical capital to the Apache Spark community. But beyond that, we're really focused on cognitive technology and cognitive open tech. So we're all about open source, really cool projects, such as detecting breast cancer. So we have a bunch of different projects going on like this that are interesting, but we'd love to move forward with this while we're here today. So we were really interested in coming up with a really interesting project around last year. We're both really interested in health. Mike used to go to medical school, and I used to work in health policy. So we're very passionate about this, and Mike came across this contest where he discovered the data set and has now been working on it.
Thanks, Madison. All right, so with that intro in place, let's get into the actual problem. So like we said, we're working on a problem for mitosis detection using deep learning. And so here we have an image of a piece of breast tumor tissue that's been sliced up, stained with an agent to show off different cellular structures, and then placed under a microscope to be examined by a physician. And so the goal in this case for a physician, when they get this kind of piece of tumor tissue, is to be able to classify the severity of this tumor, right? Because a tumor in a patient can be either relatively benign, and that may be a good prognosis, or it can be relatively malignant, and they may need like further treatments or other further aspects. And so it's a difficult process and very important one. And so for breast tumors, usually the first subtask that a physician in this case will work on is to identify and locate all of the cell mitoses in a region of the tumor. So this image kind of represents a region of the tumor that a physician might see when they look under a microscope. They'll see like the smaller portions and scan around for that region. And so they'll look through this, and if you look at this little tiny blob that we're pointing to, and it's enlarged to the left, that is a cell mitosis. And so without getting too much into the details, like medical details for it, when cells undergo mitosis, that's the process of cells dividing. And so in other words, it's the way that tissues grow. And so when they do that, the DNA inside the nucleus, it unravels. Otherwise, it's very faint and very tightly wound, so you don't see it as well. Unravels, it takes up most of the nucleus, they peel it apart so it can be replicated, and then the cells will pull apart each with a pair of the DNA. And so it does that. Our stain that we have on the tissue will stain these nucleic acids a dark blue. And when you see this mitosis right here, instead of just being a round circle that mostly is pink, a little bit of blue, we see a very big blue blob. And to a trained physician, they'll say, oh, that's a cell undergoing mitosis. If you look in the center, it's actually a particularly interesting case. You can see a cleft in the center where the cells are starting to pull apart. So it turns out there's actually a few other mitoses here as well. And they have different characteristics depending on when this tumor tissue was biopsied, as well as like, the three-dimensional aspect and the way this was sliced. So it's a difficult process. And despite extensive training that a physician in this case will receive, it ends up being prone to issues of subjectivity. And so the challenge here is to develop an algorithm that, given this image of the tissue, could automatically detect those cell mitoses, and thus kind of aid the physician in their ability to treat. And so we're treating this problem as an image object detection problem, and we're working on a deep learning approach involving convolutional neural nets. So this is kind of a general outline of our approach. So imagine we have these raw images of the tumor tissue with locations of the cell mitoses. And based on the fact that we have relatively few images and the mitoses of interest are relatively small on the image, rather than a large region like a cat or dog image, we're electing to generate versions of the data set where we cut up the images into tiles, and then we make use of pre-trained convolutional neural nets, PGTs, ResNets, whatever. We modify them slightly. We'll fine-tune various regions of those models. During training, we'll make use of data augmentation, kind of the standard practices. We actually make use of trained models to go back and bootstrap the generation of data sets that are more difficult to train on. And then we'll also make predictions for the actual coordinates of what we believe to be the mitosis locations. So a lot of interesting aspects. We're going to save the details for that future talk, so this will just serve as a teaser, and we'll go deep dive into the algorithms, the math, and all that aspect of it next time. And so for the next few minutes, I actually just wanted to, since we don't want to get into pieces of that, as it'll take a long time, I just wanted to pull out one aspect to kind of like leave as a nice takeaway that I found to be useful for working on machine learning problems. And that's having a good experimentation workflow. So kind of the way I see it, machine learning is science, in the sense that we come up with ideas or questions that we aim to explore. Right? So in our case, it's mitosis detection. And then we create hypotheses, right? These are what type of model, what kind of general approach do you want to take? Do you want to use regularization or what particular architecture, et cetera? And we design experiments that we actually want to run so we can test these hypotheses, right? So these are the actual code that we're training our models with. And so we run these experiments, we evaluate them singularly, and then we compare them with each other, right? Both in the current and as well as past experiments. And this process continues in a loop, where you're constantly refining hypotheses, you're designing new ones, you're designing new experiments, running them, comparing results. And ultimately, this continues until you reach, you achieve kind of an end goal that gives you a satisfying answer or conclusion to the original problem or idea that you set out to explore. And so overall, I found that just in general, having a good workflow to support this type of experimentation is extremely useful for trying to achieve success on a machine learning project. And so with that in mind, I just thought I would real quickly kind of go through just kind of the components that I found useful. And the kind of key takeaway here would be, yeah, the specifics might be interesting, but maybe just next time if you're approaching a machine learning problem, maybe think about having a workflow so that you can focus more time on the problem itself and the math. And if you're building tools or services to support machine learning, maybe think about, can this help improve someone's workflow, or does it fit in nicely to conventional workflows? So for me, and I think all these aspects, may not, the specifics are towards me, but the aspects may be more broader. Up on the left, just so we have some context, this left-hand side is a terminal, this is a TensorBoard window on the right. On the left-hand side of the terminal, there's a local file. Upper right is a local terminal. Middle right is a terminal on a remote server, and bottom right is a local file. And so kind of the number, I have 6 pieces to my workflow. And the first piece is an experiment journal. And so I think this is probably one of the most important pieces to me. So that's kind of this local file in this bottom right. And this is a journal where I keep track of everything. So I keep track of hypotheses, right? What am I trying to experiment with? I keep track of the experiments themselves. How did I run the experiments? Where are the experiments running? Which machine are they running on? How did I start running this experiment? Importantly, what are the goals for this experiment? Like, why am I running it, right? That's a part of the hypothesis. And when you have experiments that take multiple days and you're running multiple in parallel, it's useful to be able to remember why did you start this experiment. And then I'll also have results as well, right? So once these experiments are complete, not necessarily track every single numeric aspect of it, because there's other ways to track that, but I will keep track of just at least a written description of the results. What did it achieve? Did it achieve or make any progress towards the goals I had for that? Did it uphold the hypotheses or not? And I maintain all that in a file so that I can quickly see what I've been working on, what's currently being worked on, what's worked on in the past, and I can go back and compare or restart experiments that are slight modifications of previous ones. So I use a markdown file for that. I think there's possibilities to expand that more into a service, or maybe even embed it in, say, a TensorFlow or a TensorBoard, rather. But just that meta idea of having a journal that you keep track of things is useful. So then, like, once I say I have this experiment designed, right, I have some hypothesis I want to test, and I've designed some experiments, I'll actually go write the code for that, right? You need to have the code so you can run. And so I tend to do development locally on a machine, and so I'll write down any code I need to be able to run that experiment. I'll test it locally, maybe write unit tests, or just run it, make sure it has the behavior that I'm hoping it will have, maybe debug it, make sure it's outputting the appropriate logs that I'm hoping it will have. Any running I do locally will be more proof of concept, because these are very expensive models, or I might use a base, like a dummy model, just to make sure the rest of the algorithm is working. And so once I have that kind of done, so I'll be writing stuff and running stuff up here, I'll have a set of GPU servers. So it's interesting going after the previous talk, because it opens up some interesting possibilities. But I just have a set of raw GPU servers that I manage myself. And so I will push the code for whatever experiment I want onto the servers. I'll make note of which server I'm using at that moment. So once again, it's kind of keeping track of what I have. Having a system that maybe manages that for you could be very useful. nonetheless, I'll throw it up there. And so once it's on there, I found it's very useful to have some system in place that will let you run the experiments and keep them running in the background so that you can detach from them, walk away, come back at some other point in time, reattach and monitor, or even kill the experiment depending on the progress of it. So currently what I use on raw servers is tmux, just to have ability to create sessions, attach to them, detach as needed, and reattach at a later point. You could imagine have a different service that did this for you and managed it for you. And then during experimentation, I do make heavy use of logging. So logging out basic things like statistics that I'm interested in. So F1 scores or loss values or different metrics that I'm interested in actually optimizing. So that's kind of what you can see on the right here. We'll talk about that in just a moment. And also we'll put model checkpoints. I'll actually put out the code that I use to run this experiment, basically everything I need to be able to evaluate that experiment and rerun it if I need to. And so I found that, given all that stuff you've logged, it's very useful to have a process in place that will let you explore that running experiment in real time, as well as compare it to past experiments. So for this project, I've been using TensorBoard. The project itself uses TensorFlow, so it's natural to use TensorBoard. Luckily, you can use TensorBoard from other projects as well. But I found it incredibly useful because you can monitor experiments in real time, which could let you go kill experiments if you no longer decide you need them. But also lets you compare them with previous experiments, and you can select whichever ones you'd like to compare with at that moment. And so that's what you can kind of see here. So you see F1 graphs here with, and I'm writing training and validation evaluations for that metric. Just in general, though, having that ability to do it in real time is useful. So that's kind of generally the workflow that I have, just a way to keep track of experiments, develop the code you need to run them, have a system in place so that you can throw them onto a server to run, and have a way to evaluate and see them in real time or compare. So I just thought that would be a nice takeaway. So once again, if you're thinking about working on machine learning, maybe just think about a workflow so that you can focus more on the problem and the algorithms. And if you're working on tools or services, maybe think about how you could enable someone to have it easier